Okay, a really short video on how Octave represents polynomials, and then also working with polynomials in Octave. Um, so actually, Octave just works with numbers, vectors, matrices. It's really good at that, but a polynomial like the one shown here, ax cubed plus bx squared plus cx plus d, this is an algebraic expression, a symbolic expression. So there are tools that can work with this directly, called symbolic algebra tools, Mathematica, um, uh, MathCAD, Derive, um, Wolfram Alpha, all of those are tools that can work, that can do symbolic algebra or do symbolic mathematics. MATLAB and Octave actually have a symbolic toolkit, but they're primarily used for numerical analysis, working directly with real data. But they can work with polynomials. They actually represent a polynomial, and MATLAB is actually represented by its coefficients. So the length of the vector actually determines the order of the polynomial. So in the first element, well, let's start on the right-hand side. This represents the constant element. This would represent the coefficient of the x element. This would represent the coefficient of the x squared element. So this polynomial, this vector of length 3 would represent a polynomial of second order. The order is always one less than the length of the vector. So it'd be x squared plus 0x minus 2, or this would be the corresponding polynomial. You can't leave out the 0. The vector 1 minus 2 would represent a different polynomial. It would represent the polynomial x minus 2. So you have to include the zeros. Even for a case like this, where we want to represent a third order polynomial, so no constant term, no x term, no x squared term, and the x cubed term is multiplied by 2. But again, we need this full vector with these zeros to represent this 2x cubed polynomial. If we just tried to represent it as 2, instead that would represent the constant 2. But so this is the basic representation. Understanding this is key to working with polynomials in MATLAB Octave. We can get the roots of a polynomial using the roots expression. We can convert from the roots back to the polynomial coefficients using poly. And then another very valuable function is we can use the polynomial coefficients, its representation, and then use the polyval function to evaluate it at a single point. So this would evaluate this polynomial at the value of x0, and then return the value of that polynomial at that point. The argument here can also be a vector, in which case polyval will evaluate the polynomial at all of those x values and return another vector of the same length. So kind of illustrate this in a little script here, where I formed the polynomial. So the polynomial I decided to work with is x squared minus 3x plus 2. That factors as x minus 1 times x minus 2. So the roots of this polynomial would be x equal 1 and x equal 2. Okay, those are the x values of which this polynomial expression is equal to 0. So in Octave, we represent that polynomial by its coefficients. So the constant term is 2. The term multiplying the x is minus 3, and then the term multiplying the x squared is 1. So first thing I do is calculate the roots. So this should be, r should be equal to 1 and 2. And then I reconstruct the polynomial from its roots, just to show you how poly works. So P2 should be the same as P, 1 minus 3 and 2. And then notice I've left the semicolons off. So when I run this script, the script will display the values of r and P2. I evaluate the polynomial at x equal to 0. I just chose 0 because that's simple. At x equal to 0, the polynomial is equal to 2. 0 squared minus 3 times 0 plus 2. So P0 should be 2. And then finally, I want to plot the polynomial. So again, in order to plot, I need vectors. So I decide to plot over the range from 0 to 4. So I need I could use linspace to do this. Again, I tend not to use linspace. It's convenient, but I tend to form vectors using colon notation. So this is going to give me what, 40 points, 41 points. 0 to 4 in increments of 0.1, so x would be a 41 element vector. It could decrease the step size to 0.01 to get a 400 points. That would give me a smoother curve. So these are the x values at which I'm going to evaluate the polynomial. Now I could separately call y equals polyval px and put y in here, but I don't have to do that. I can use as the argument to a function another function. Okay, in this case, I know polyval when I evaluate the polynomial at this value of x, is going to return a vector y of the same length. So I actually just use that as an argument. Octave will first evaluate this function call and then use the return value here when the plot function is called. And I use this grid on function. I don't think we've talked about that previously in the plot. It'll show it'll put a nice rectangular grid on the plot. So I'll show you that. So let me run this. So here's the graph of the resulting plot. And so you see the grid lines on here at the tick marks. And in particular here, I put the grid line on so we could follow the 0 line. And certainly it looks like the points at which the polynomial is equal to 0 are at x equal to 1 and x equal to 2. And those are the roots of the polynomial. So this is the graph over the range from 0 to 4, because that's the x range I picked, of this polynomial, x squared minus 3x plus 2. Now, if I look back in the command window, I'm going to find r and p2. R are the roots, which again are 2 and 1, and then p2 was just, again, reconstructing the polynomial from its roots. And I see there I get the same polynomial vector 1 minus 3 and 2. And then p0, if you recall, I just evaluated the polynomial at x equal to 0. I could evaluate it at a bunch of different points, but and I indeed do that here when I pass it a vector. Okay. The other thing that you can do, there are lots of different things you can do with polynomials. You can multiply polynomials. That corresponds to actually what's known as a convolution operation, but you can multiply two polynomials together to get what the resulting polynomial would be. You multiply. You don't multiply the two vectors. That's not equivalent to actually multiplying the two polynomials. The operation's a little more involved than that, but you have that capability. The only other thing we're going to do though is looking at fitting polynomials to a given data, and the polyfit command does that. So actually, so you could type this in. I put this slide into a script. So same x and y that's on the slide. Okay, and then actually I extended it a little bit. I found the best first order polynomial, and a first order polynomial is going to be a straight line. So this is going to be the best fit line or the regression line that best fits our xy data. And then P2 then corresponds to the best fitting second order polynomial. And so then here in the plot, I plot the three xy points in black using circles, so just markers here. I'm not connecting those 3 points by lines. And then over the region from -3 to 3, I plot my P1 polynomial using polyval. okay, to evaluate this polynomial at these x locations. Plot that in red. This is going to be the best fitting line. And then this is the best fitting second order polynomial. Again, I could find the best third order polynomial. Actually, beyond that, it's going to be, because I've only got 3 points here, beyond that, a third order polynomial is going to go exactly through the 3 points. So, but for first and second order, it's going to be the best fitting polynomials to the data. And then again, show the grid, and then show actually here when I run the script. I could have just left the semicolons off to show P1 and P2, but I did it differently here. This is just going to display P1 and P2 when I run the script. So first, let's run the script. That's actually produces this new plot. So here are the 3 data points, and here's the best fit line through the data points. And actually, the second order polynomial appears to go through all 3 points. So the 3 points must have been chosen to fit a set. So you need 2 points to determine a line. 3 points will uniquely determine the second order equation. So you just need 3 points to determine this second order polynomial that will. So we can always find a second order polynomial that goes exactly through three equations. If we look back at the command line window, I'll see these are the coefficients of that line. So this is the x coefficient, and this is the constant or the y offset. Correspondingly, this would be the slope of the line. This would be the y offset, the 0.28. And then these are the coefficients of the second order polynomial. Again, this middle term is really small. I mean, it's theoretically, I'm guessing that the expression for the polynomial is actually x squared minus 1. And the x term here is essentially 0. It's so small in comparison to the x squared and the constant term that it's essentially going to have no effect on the polynomial. So, very quickly I've got, expressions for the best fit line, the best fit polynomial. And we can go back and look at the graph. I think the slope here is supposed to have a slope of 1.14 for the line, and then it's supposed to have a y offset. So here's 0, here's 2, 1. It appears, the y offset is 0.28. Okay, and then if this polynomial really is, x squared minus 1, the second order polynomial, that would actually have roots at x minus 1 and x plus 1. And so we can see those here, that here's the root at x minus 1, and then we have another root at x plus 1 for the second order polynomial. Okay, so here's a little exercise. Pause the video at this point if you want to do this. Okay, I'll show you now, my solution for doing this. So here's the exercise. Let me blow that up a little bit so you can see it. So the first thing we were asked to do is form a vector that's going to be, our x variable that goes from -4 to 4 and increments of 0.1, and then compute y, which is the square of x. This would exactly fit a second order polynomial actually with a coefficient of 1, but what we're going to do is add some noise to that data. We've used rand in the past, which returns a uniformly distributed random number between 0 and 1. Rand_n returns a normally distributed random variable with mean 0 and a standard deviation of 1 by default, but you can change those. So we plot the x and y data, the noisy y data, using markers. So this is what looks like about 81 points there. And then I find the best fitting second order polynomial to the data, and then plot that data, and then actually also when I run this, I print out the coefficients of the polynomial. So if you run this, Here's the resulting plot, showing our noisy y data for the different x values, and it looks like we've found a good second order polynomial that runs through our data. Again, if I look at P2, I get the corresponding coefficients of that, the coefficients of that best fitting polynomial. So it's 1.03x squared plus 0.008, or about 0.01x, and then plus a constant term of 0.12. And theoretically, y is just equal to x squared, and so the P2 theoretically should be 100. But with the added noise, I don't get actually that exact theoretical result. Every time I run this, because I'm adding random data, I'm going to get different. I ran the wrong thing. I'm going to get different set of numbers every time I run this. But for all of them, that x squared coefficient is about 1. I'm also getting a slightly different plot every time. Actually, I have hold on. That's one of the issues. If I don't close the graph window, that all the plots kept being added to the original plot. So the way around that actually is just to put hold off at the end to ensure that doesn't happen. So again, every time I run this now, I'll get a slightly different plot because of the random data. The points will change slightly.